In the last video we learned what a function was, and now we're going to look at some properties which a function may or may not have. First of all, I need to talk about a definition which is that of the image of a function. If you have a function f from a set x to a set y, so the domain is x and the codomain is y, then the image of f, which we write like this, is the set of all things of the form f of little x, where little x is in big X. So the image of f is then a subset of the codomain. So in this case, with our notation, it's a subset of y. But it may or may not equal the codomain. So it's important to distinguish between the concept of image and the concept of codomain. Those are distinct things. They may or may not be equal. Just as an aside, you'll hear some people talk about the range of a function. I will never use the word range in 0007. It's confusing because some people use range to mean image, other people use range to mean codomain. So it's confusing, we don't need it, we will never say it. Let's look at some example ranges then. So beginning with this example, I have f, which is a function from the real numbers to the real numbers, and its rule is that f of an input x is x squared. Then the image is the set of all things which are equal to the square of a real number. Now every real number, the square of every real number is greater than or equal to 0, and in fact every real number which is greater than or equal to 0 is a square. So that means the set of things in the image is exactly the set of non-negative real numbers, which we write using this interval notation which I defined in the last lecture. So the image of f here will be the set of all non-negative real numbers, and that is a proper subset of the codomain of f, because the codomain was the whole set of real numbers. Again, let me emphasize, when you define a function, you have to say what the domain is, and you have to say what the codomain is, and you have to say what the rule is. You can't work those things out. You can't work out, just given a rule, what is the domain and what is the codomain. Those are part of the definition, and if you don't write them down, you've not defined your function. So this was an example where the codomain was different to the image. In fact, the image was a proper subset of the codomain. Let's take another example. So here g is a function whose domain is the set containing 0 and 1, and whose codomain is the set containing 0 and 1. And the rule is that g of 0 is 1 and g of 1 is 0. Then the image of g, well in this case we can actually list the image of g. I mean, the image of g is the set of all things you can get by applying g to an element of its domain. In our case, the domain is only the set 0 and 1, so I can just list the two things in the image, which are g of 0 and g of 1. So in our case, that's equal to 1, 0, and that is also equal to the whole codomain. So g is an example of a function where the image was equal to the codomain. Of course, remember, it doesn't matter what order we write things in when we're talking about sets. The set containing 1 and 0 is equal to the set containing 0 and 1 because they've got the same elements. Our first function property is the property of being surjective or onto. The definition of surjective or onto is that a function f with domain x and codomain y is surjective or onto if and only if, for each element b in y, there exists an element a in the domain x such that f of a equals b. There might be more than one such element a, there might be infinitely many, but there has to exist at least one element for each b such that f of a equals b. Now we could rephrase the definition of being surjective or onto using the image as we defined it on the previous slide. Another way to define surjectivity would be to say that f, a function with domain x and codomain y, is surjective or onto if and only if its image is equal to its codomain. So the function g, which we saw on the last slide, was surjective because its image was equal to its codomain, and the function f from the last slide was not surjective because its image was a proper subset of its codomain. Let's look at some new examples here. So actually, this first one is actually the same one that we saw before. F is a function whose domain is the real numbers and whose codomain is the real numbers, and the rule is f of x equals x squared. It's not onto because there is an element of the codomain, namely -1, with the property that there is no element of the domain such that f of a equals minus 1. That's just a standard property about real numbers. There's no real number whose square is equal to minus 1. Therefore, there's an element of the codomain which is not in the image. That means that f is not onto or not surjective. Now let's make a very small change in the function f from the first bullet point. We'll give it a different name because it's a different function. So this time g has domain the real numbers and codomain the set of non-negative real numbers. So the interval closed at 0 and open at infinity. The rule is that g of x is equal to x squared, and this is onto. So in order to check that it's onto, you need to check that for every b in the codomain, that is for every non-negative real number b, there exists a number a in the domain such that g of a is equal to b. And specifically, for every b in the codomain, the number square root of b is in the domain, and g of the square root of b is the square root of b squared, which is b again. So notice that this argument only worked for the function g. It doesn't work for the function f, because for the function f, there are elements of the codomain which don't have a square root in the domain. If you take minus 1, it doesn't have a square root which is a real number. If we move into the complex numbers, okay, it's got a square root, but there is no square root for minus 1 in the domain of f, and that's why f is not onto. Whereas for g, every element of the codomain has a square root in the image, and g maps that to the number you first thought of, so g is actually onto. Let's think about these function diagrams which I introduced. You remember that we had a way of drawing a diagram for a function, which was that we drew some dots to represent the domain and some dots to represent the codomain, and we drew an arrow from an element of the domain to where this function sends it in the codomain. So for example, if we drew examples of our function being x squared, and we drew some arrows to show that minus 1 was sent to 1 under the squared function. So let's think about a diagrammatic interpretation for this concept of surjectivity, or concept of being onto. So in diagrammatic terms, so we drew the codomain, we drew the domain and we called it x. We drew the codomain and we called it y, and we illustrated the elements of the codomain by dots. And we showed where the function f sent a particular element of the domain by drawing an arrow from x to f of x, like this. Well then, a function like this would be surjective or onto if and only if everything in the codomain is the target of an arrow. The target means what it's pointing at. So here this arrow x, this arrow starting at x, points at f of x. F of x is the target. So that's what it means for a function to be onto. Every element is the target of at least one arrow. It might be the target of more than one arrow, but it's got to be the target of at least one arrow. Okay, let's move now on to injectivity. So this is another function concept. Function f with domain x and codomain y is called injective, or one-to-one, if and only if, for every a and b in x, if f of a is equal to f of b, then A must be equal to B. Let's look at some examples of injective and non-injective functions then. So returning to the same example as on the previous slide, if you have f, the function whose domain is the real numbers and whose codomain is the real numbers and whose rule is f of x equals x squared, that is not injective because there exist two different things in the domain which get sent to the same thing in the codomain. For example, and there's infinitely many different examples, but just one example is enough to show that it's not injective. 1 is not equal to -1, but f of -1 is equal to 1. So f is not injective. On the other hand, let's look at a closely related example to see how injectivity depends very carefully on what the domain and codomain are. So we will take h to be the function from the set of all non-negative real numbers to the real numbers, with the same rule as before, h of x is equal to x squared. Now this function is injective because there's a word missing here. If h of x is equal to h of y, and x and y are elements of the domain of h, then actually x must equal to y. Right? If you've got two non-negative real numbers with the same square, then they're actually equal. So this argument doesn't apply to f because because the domain of f contains, for example, 1 and -1, which have the same square, and 2 and -2, which have the same square. But the domain of h does not contain two different numbers with the same square. So h is injective because of that property, whereas f isn't. So it's very crucial that you think of a function as a whole. When you're thinking about a function, you must think about the rule and the domain and the codomain if you're going to determine successfully whether or not it has these properties of injectivity or surjectivity. Again, let's think in terms of our diagrams. So diagrammatically, I'm going to draw the same diagram as I always do, so some dots to represent elements of x, the domain, and some dots to represent elements of y, the codomain, and I'm going to draw arrows to show the image, the output of the function given an input in the domain, so perhaps it looks like this. And of course there has to be an arrow starting at every element of the domain. I've not finished drawing my function. I've just drawn some of the arrows. In order for it to be a function, there must be an arrow starting at every point in the domain x. But in terms of diagrams, a function is injective. Well, can you see what the condition is in terms of arrows? Pause the video and think about it. The answer is that no two different arrows have the same target. The target means what they're pointing at. So take our function f on this slide, for example. Well, here is -1, and here is 1 in the domain, and here is 1 in the codomain. And look, there are two arrows pointing at the same thing. It has failed to be injective, failed to be one-to-one. Finally then, our final definition is of a bijection. And the definition is that a function f is bijective if it's both surjective and injective. So both onto and one-to-one. And the definitions are that, so some examples are, the function g we met right at the start is a bijection. So g, the function with domain, the set containing 0 and 1, and codomain, the same set containing 0 and 1, such that g of 0 is 1 and g of 1 is 0 is a bijection. And we can simply draw this. Let's draw it to see what's happening. So here is the domain 0 and 1. Here is the codomain 0 and 1. And the rule for our function is that 0 goes to 1 and 1 goes to 0. You can see that it's onto because every element of the codomain has an arrow pointing to it. Every element of the codomain is the target of some arrow. And you can see that it's 1 to 1 because there are no two different arrows pointing to the same place. That means this has both of the properties of surjectivity and injectivity, so it's a bijection. And there's another example, an important example. For any set X, the identity function is a bijection. Right, it is 1 to 1 because if idx of little x equals idx of little y, then, well, by definition of the identity function, x equals y, so the identity is 1 to 1, and for any b in x, there does exist an element of x such that the identity applied to that element is b, because of course the identity applied to b is equal to b. So the identity is onto. Let's add that conclusion up here. It's 1 to 1, it's onto, so it is a bijection. No matter what x was, it's a bijection.